In 1869, a Russian chemistry professor named Dmitry Mendeleev observed that certain groups of elements had similar properties. At that time, the periodic table as we know it today did not exist. There were a bunch of elements that we knew about, but there was not really a universal organization of them. So what he found was that if you listed the elements in order of increasing mass, those similar properties recurred in a periodic or repeating pattern, and this periodic is where the table gets its name. So down here, we've got the first 20 elements in order. And you could think of this a little bit like a piano keyboard, where this is C, and up here is C, and then there's another C. And they're not the same note, but they're harmonics of each other. They're related to each other, right? And so the green ones here share some common properties, the blue ones, the purple ones. And so this became summarized as the periodic law, which just says that when the elements are arranged in order of increasing mass, certain sets of properties recur periodically. So he organized the elements that were known at the time into a table with rows and columns so that elements that had similar properties fell into the same columns. His table had some gaps because there were several elements that had not been discovered yet. And he predicted that elements would be discovered, and he also predicted the properties of those elements based on the properties of the elements nearby. So here are the first 20 elements put into a very simple periodic table. We'll find that hydrogen is kind of an exception to everything. I think of him as the baby brother of a very large family. And I don't know what happened in your family, but among my kids, the youngest one he's sort of like a free-range wild thing, right? We were too busy and too tired to do anything with him. So, he's an exception to all the things, right? So this is a baby brother, gets away with stuff that nobody else in the family would get away with. So in some respects, hydrogen should be over here with the other orange elements. But there's some other ways in which hydrogen acts like the blue elements, and so he just kind of sits there by himself. These guys have similar properties, these guys, and these guys. So this is a table showing time of discovery. So all of these lighter yellow ones have been discovered since 1950. A lot of these are man-made or very unstable. So the ones that would have been around in Mendeleev's time would probably have been all the blue and purple ones. Some of the light purple ones were being discovered during his lifetime.
One of them's in California.
Yes, there's a Californium. Yeah. So, that's a whole nother topic. But there's, down here, I almost did that again. Down here, ES is Einsteinium, named for Einstein. Berkelium, named after Berkeley, California. Nobelium, Nobel Prize. So all of these guys down here, there's some meaning to their names. Here they were kind of going in a uranium and neptunium, plutonium. They were kind of doing a planet thing there for a while. I don't know. A lot of the older elements also have meanings from their names, but because a lot of it's Greek or Greek, I guess. It does. Latin is the other one. It doesn't make a lot of sense to us. So sodium, its Latin name was natrium, and that refers to from the ocean. So lots of interesting things in there. This is how, in 1869, Dmitry Mendeleev completed the first periodic table. Have you guys even seen the game of Tetris?
Yeah.
Yeah, okay. I really should take that one out. It never gets much of a reaction. I thought it was funny. In the modern periodic table, instead of increasing mass, they are ordered by increasing atomic number. And what is the atomic number again? Number of protons. Okay? And then our modern periodic table also contains more elements because more have been discovered since his time. There's a lot of information in the periodic table. There are different sections, there are a lot of trends, and we're going to learn about those as we go through the semester. So here we have a periodic table, and we can look at major divisions highlighted by the different colors. So metals, all of these yellow ones are metals. So you can see that most elements are metals. Over here in the green are the nonmetals, and they're all clustered together in this corner. And then we've got the guys that are kind of in between. They're called metalloids, just like a humanoid is kind of like a human but isn't, right? They're also sometimes called semi-metals because they have properties of metals and of nonmetals. And we find these in between the nonmetals and the metals. There is a stair-step line here. On most periodic tables, it's just a bold line. This table didn't come with that, so we used blue tape and made it because we need the line. That is the line dividing the metals and the nonmetals. So you should be able to identify an element as a metal or a nonmetal just from its position on the periodic table. So what about these semi-metals? Well, polonium is a metal. I would never ask you about that one. Aluminum. Is aluminum a metal? Yeah, you probably have an aluminum pan or cookie sheet or something at home is definitely a metal. But everything else that is touching that line is a semi-metal, if that helps. We also have two things that are pulled out down here. The periodic table on the wall is actually what it's supposed to look like. So if you look at the atomic numbers, here we go, 55, 56, 57, 58, and it just continues in the row. Whereas on this periodic table, you have to jump down here. So what'd they do that for? I don't know for sure, but I think it's just to make it fit on a piece of paper better. We don't use these guys very much, and if you pull them out, you can have a bigger periodic table and be able to read it better. But these guys, as this arrow shows, these guys are supposed to be inserted into there. And then this is giving you pictures of some of the elements that you might be familiar with. So we classify elements as metals, nonmetals, or metalloids. And we should have, I'm not going to quiz you and see if you know every single property of a metal, but we should be able to recognize metals from a description. And these we should understand from just being alive. So metals are good conductors. What do they use for wires to conduct electricity? Metals, right? Metals are malleable and ductile, and those are words you're probably not familiar with. Malleable means that if you take a chunk of it and you hit it with a hammer repeatedly, you can flatten it. It won't crack or shatter. It'll just kind of smush out like really, really hard Play-Doh. Ductile means it can be pulled into a wire, and those are properties of metals. Most metals are shiny, and the thing that matters the most for chemistry is that they tend to lose electrons when they undergo chemical changes. If an atom loses an electron, what kind of an ion does it become? A cation, a positive cation, right? The nonmetals are like not metals, right? So everything the metals are, they're kind of the opposite. They're poor conductors. They're not ductile. They're not malleable, and they gain electrons. So if you're gaining electrons, what kind of an ion does it make? An anion. So nonmetals form anions. Nonmetals form negative ions. And then the metalloids, or semimetals, several are classified as semiconductors. You might have heard of semiconductors. They have mixed properties. The cool thing about semiconductors is that their electrical conductivity is like between metals and nonmetals, and it's very dependent on temperature. And so you can change the conductivity of that. And there's a whole bunch of other things you can do that make semiconductors just super valuable. So here's our stair-step line. This one is not colored for metals and nonmetals, but different areas or blocks of the periodic table. So in the yellow, which is these guys here and these guys over there, those are considered the main group elements. Main group elements tend to follow patterns better than the transition elements. The transition elements are the transition between this side and that side, right? So the parts of the periodic table that stick up are the main group elements. We call the rows periods. I don't have a good explanation for that. And we call the columns groups or families. Remember how Mendeleev arranged the elements? Elements in the same column had similar properties. So elements in the same group or family have similar qualities. So the periods are numbered 1 through 7, and the groups, there's 2 different sets of numbering. There's the American numbering, and then there's like what everybody else does. I like the American method, and we're in the United States, so we'll go with that. So the current U.S. usage is to just number them 1 through 18. I'm sorry, that's backwards. That's the way that it officially goes. The U.S. usage is with the letters. So this is 1A, 2A, 3, 4, 5, 6, 7, 8A. So we've got an A after main group elements. And the transition elements have B's in their group numbers. Now, you may think, well, this is kind of weird. It goes 3, 4, 5, 6, 7, 8. There's 3 of them, and then it goes 1 and 2. We're not really going to use those group numbers at all. But the group numbers for the main group elements are very helpful. And so here, the numbers are the same. Over here, 3A is 13. 4A is 14. So if you just ignore the 1, you've got the group number. Any questions? Yeah.
Why do the bottom elements not match up with those? They got different. The 118 was low.
That's a good question. So the periodic table on the wall has a different symbol for number 118. It's UUO. And I can never remember how to pronounce that. But basically, it's like Latin for unnamed thing number 17 or something. So older periodic tables, you'll see a bunch of these with symbols like that. UU and a letter. I don't remember how long ago now it was. It's recently, within the past 5 years, I think. They named a whole bunch of new elements and published them in a new periodic table. And so a lot of these guys down here are new. Their names are new. And so this is an older periodic table, and it doesn't have all of them. It's a great question. Anybody else? Something that's on the wall periodic table that's not on this one, you'll notice the element symbols are in different colors. There's black ones and blue ones and red ones and white ones. The white ones are very unstable. They're not naturally occurring. The red ones at room temperature are gases. The blue ones are liquids. There's only two. Mercury, which is a very strange liquid metal, and bromine, which is a liquid nonmetal. And all the rest of them, all the black ones, are solids at room temperature. Yeah? Not on the memorization quiz, no. They're listed up there. I mean, it's cool that people have made them and everything, but a lot of them, they can't make enough of them, enough atoms to even see what color they are or find out how heavy they are or anything. They've just got this very brief evidence that, yes, we made that, and then it falls apart. So they're really not useful for anything. And so, I mean, their names are kind of interesting, but no, those guys aren't going to show up. The elements on the memorization quiz are mostly these guys and some of these metals. It's the ones that we're going to run into more often. If we have anything else, like if we end up needing niobium on an exam, I would give you its symbol and its name. I would not expect you to know that. Yeah. Mm-hmm. Yeah, so I will give you a periodic table in case you don't like to keep looking at the wall, or maybe you forgot your glasses, you can't see it today. And there's a copy of that on Canvas. You can see what periodic table I will give you. It's not going to have element names, but it will have their symbols, all the group numbers, period numbers, the stair-step line, and atomic numbers, and then all the masses, average masses. Yeah. Yeah. That's a good question. Should we use the mass that's on the periodic table that we're given, or should we use the one on the wall? So, if you follow significant figure rules, it shouldn't end up mattering. And if it does, it should only be in the last digit. So it shouldn't be a problem. What is important to watch out for is some people get into the habit of rounding all these average atomic masses to whole numbers. Some of them are whole numbers. Like to 4 sig figs, oxygen is 16.00. But chlorine is 35.45. That's like between 34 and 35. And so you drop that off, and now you're going to start to see some differences. So always use 4 sig figs, at least, in your masses. Yes? Mm-hmm. Why would they want to what? Why would they want to create it? Just to see if they could. Yeah. Yeah, there's a whole group of people that are like, tell me I can't do something, and I'm going to go out and prove that it can be done, right? And, we learn things about that. Is that, really practical research that they're doing? No. But it's pure science, right? Science just for learning's sake. And when we pursue pure science, we often find things that have practical uses. So, yeah, not much benefit in those guys. Any other questions? So some of those groups, the columns, have names. Okay. The groups, again, the elements have similar properties. And so these are some group names that you should remember. The noble gases. All those elements in group 8A or group 18. Helium, neon, argon, krypton, xenon, and radon. Notice they're all red, they're all gases at room temperature. Those are the noble gases. They're very unreactive. And so when I see the word noble, I think of like the king and queen, right? And, you know, they're kind of apart from all of us regular people. They don't interact with us, right? So the noble gases are kind of like that. They're kind of snooty, and they just don't have much to do with anybody else. Over on the other side, in group 1A, are what are called the alkali metals. And these are all quite reactive metals. So like sodium, potassium, rubidium, those will react fairly violently with water. And so if you want to keep sodium in the stockroom, you have to keep it in a jar covered with oil so that no water, even water in the atmosphere, can get to it because it will just react. Very, very reactive. Right next to those are the alkaline earth metals. Alkali and alkaline both refer to something that's not acidic but basic. And so these make basic solutions when they react with water. But in terms of where the earth thing came, I don't know exactly where those names came from. It's what they are. These guys are fairly reactive, but not as much as the alkali metals. And then jumping back to the other side of the periodic table, the halogens, group 7A, those are all nonmetals, but they're also very reactive. So noble gases, alkali metals, alkaline earth metals, and halogens. If we look at main group metals, metals tend to lose electrons and they form cations, and the main group metals do it in a very predictable way. So they're going to form a cation with the same number of elements as the nearest noble gas. And what that means is they will end up with a charge that is equal to their group number. I need a periodic table. So over here is lithium. The lithium atom has 3 protons and 3 electrons. The closest noble gas is helium with 2 protons and 2 electrons. If lithium loses 1 electron, then it will have the same number of electrons as a noble gas. And it turns out that is more stable. Here's magnesium. Magnesium's closest noble gas is over here. Neon has 10 electrons, magnesium has 12. So when magnesium forms an ion, it loses 2 electrons to have the same number of electrons as neon. Well, losing 2 electrons gives you a plus 2 charge. So here's one of my, well, you decide what kind of an analogy it is. This is how I think about it. So the noble gases just kind of have it all together. These are the cool kids, the in crowd, everybody wants to be like them. And I think I've mentioned that the protons, the nucleus, is kind of like who you are, and the electrons is how you look, right? You can change your hair color, you can change what you're wearing, there's all kinds of things you can do to change your appearance. So magnesium can change his appearance by losing 2 electrons. Electrons are on the outside, and now he's walking around on the outside looking a lot like neon. And so he feels like that makes him cool. Does it really change who he is? No, he doesn't become neon, but he looks like neon. I think we all recognize that in high school and it can vary from different high schools even in the same area, but there's like this style of dress, right? A type of clothing that a lot of the kids wear, right? I'm going to express my individuality by dressing like everybody else. It's really kind of funny, and yet we all did it, right? So that's kind of how I see these guys. So let's go back to the words. So, the main group elements form cations. Most of them have predictable charge. The charge is equal to the group number. I'm jumping back to the periodic table now. So these guys are in group 2, group 2A. They need to lose 2 electrons to have the same number of electrons as a noble gas. So they will form +2 ions. And group 1 needs to lose 1 electron, and so they will all form +1 ions. Then we have over here is aluminum. Now these guys are also main group elements, but they don't behave very well, so we're going to ignore them right now. Aluminum is a main group element. What group is he in? 3. What charge does aluminum have? 3+. Because when aluminum loses 3 electrons, it has 10 electrons like neon. Okay. Later we'll learn more of a scientific sounding explanation for why they do that, but right now we're just observing patterns, which are still really useful. So main group elements lose electrons, main group nonmetals gain electrons. And they are going to form an anion with the same number of electrons as the nearest noble gas. So what is often said is the main group elements that form anions with predictable charges, the charge is equal to the group number -8. So that works for some people and not so much for other people. So here's fluorine. If fluorine wants to look like a noble gas, how many electrons does it need to gain? 1, right? So this is going to have a -1 charge. How about oxygen? To get to 10, it has to gain 2 electrons. How about nitrogen? It's gain 3 electrons. So the group number -8 giving us the charge, 5 minus 8 is -3. That gives you the charge. But let's pretend we're playing a game instead. And you're on the board game, and this is the starting point, and you roll the dice and you get -2. So you go -1, -2, because you're going backwards, right? This guy has a -1 charge. This guy has a -2 charge. This guy will take a -3 charge. -1, -2, -3. -1, -2, -1, -1. So you're just counting backwards from the noble gases. Those are the charges that those elements make when they become an ion. Any questions?
Wait, which ones are the noble gases?
The noble gases is group 8A. All these guys on the end. Yeah. What about those? Yeah, because I stopped here, didn't I? Well, carbon is halfway between, right? It would have to gain 4 electrons or lose 4 electrons. And that's just too much effort. Carbon has just resigned itself to being a nerd. It's just I'm not even going to try because I can't, right? So carbon really doesn't form ions. Yeah. So, we tell you these patterns, and I'm not going to teach you the things that don't come in to the pattern, because if you just learn the pattern, I'm only going to ask you about things that follow the pattern, right? I'm not going to ask you for the charge of a carbon ion, because carbon ions don't exist. Okay. The other thing I should tell you is I will be lying to you occasionally in Chem 1A, but it's for your own good. Because sometimes the truth is just too complicated. Yeah.
Are you saying carbon ions do exist?
I'm saying that a carbon ion could exist, yes. But for our purposes, it does not. So I qualify a lot of things, and I say, in Chem 1A, carbon ions do not exist. Any other questions? And what about these guys? They are not very predictable. So transition elements form different ions with different charges, and we'll figure out how to do them later. So in general, the alkali metals, group 1A, lose one electron and form +1 ions. The alkaline earth metals, group 2A, 2+ ions. The halogens, group 7, they're one to the left of group 8. They're -1. The oxygen family, which doesn't really have a name, group 6A, is over 2, and it makes -2 ions. Okay, so if you understand those patterns, and I'm trying to give you ways to, relate it to everyday life or something instead of just rote memorization. That never worked for me. I need to make up a reason for things. And if you don't like mine, I'd be happy to talk to you, and we can make up some other ones that'll make sense to you. The rules here are not complicated, and then it allows us to predict charges of a whole bunch of ions. So that's a really useful thing. So here's showing ions that form, or elements that form ions with predictable charges. So over here, we've got group 1A, they're all 1+. Group 2A, 2+. Why is that guy not there? Because he doesn't really participate. Just ignore him. Noble gases don't make ions. And here is the halogens, and look, hydrogen is now over here as well. It'll make a positive ion or a negative ion because it thinks it doesn't need to follow the rules. It's the baby brother gets away with stuff. All of these guys are -1. These guys are -2. These guys are -3. So the charge is to start over here and count backwards. -1, -2, -3. And notice that these guys aren't there. Aluminum is in the main group. It's a metal in group 3. Metals always form positive ions, and so aluminum is +3. So predict the charges of the monatomic ions formed by these main group elements. So monatomic or monoatomic just means that this ion is from a single atom. Those ions in your memorization list, they're polyatomic. They have lots of different ions, and they follow a different set of rules. So if nitrogen becomes an ion, what would its charge be? -3. We're going to find nitrogen here, and then we're going to start over here. That's 0, -1, -2, -3. And so if we wrote that ion, we'd write N3-. Okay. How about Rb? This is rubidium. Rubidium's down here. This is a metal. It's to the left of the stair step. And it's in group 1. So it's going to form a +1 ion, Rb+. What if you get mixed up and you can't remember which side of the line is metal and which side is non-metal? Well, pick something you know, like iron. Is iron a metal? Yeah. Well, where's iron? Iron's over here. That means that this side is the metal side. And over here, things like oxygen, which is definitely not a metal, and you never see any cars made out of oxygen. That wouldn't work very well. These are all the non-metals. Okay. Any questions?